All right, so we're right at the start time, 12 o'clock Eastern Standard Time. So let's go ahead and get started. First off, good afternoon. I'm Jason Thomas with Project Engineer at the National Center for Defense Manufacturing and Machining, and I'll be your host for today's NCDMM Alliance Partner Lunch and Learn. NCDMM has established a team of over 200 alliance partners who provide significant manufacturing expertise and technology to help solve advanced manufacturing related issues. Our collaborative approach developing and deploying best-in-class solutions is successful because we integrate the specialized and innovative skills, technologies, and practices of our alliance partner network. If your organization is interested in becoming an NCDM Alliance partner, you can navigate to ncdmm.org under Who We Are and click on Our Partners, or you can go ahead and click on the link that I shared in the chat. There you will find a link to submit your application. A few important notes before we kick off the Alliance Partner Lunch and Learn. At the end of the presentation, there will be an opportunity for a brief question and answer session. If during the presentation you have a question, you can submit that in your Q&A space on your Microsoft Teams screen, and we'll ask it during the Q&A session. I will do my best to get all of your questions answered. So today's NCDM Alliance Partner Lunch and Learn is focused on advanced materials for accelerating defense innovation with QuesTek, where some key topics will be covered, including materials and how they affect product performance, whether traditional methods are still competitive, and bring the Industry 4.0 to materials. Without further ado, it is my pleasure to introduce our speaker, Keith Fritz. Keith is a seasoned metallurgist with over 20 years of experience and a passion for manufacturing and additive technologies. As Director of Federal Solutions at QuesTek Innovations LLC since 2022, Keith leverages his deep expertise in material science to deliver tailored engineering solutions for defense, aerospace, and industrial clients. His innovative leadership helps clients overcome complex material challenges, driving superior performance and cost savings through advanced materials design. Before joining QuesTek, Keith served as Director of Technology at ASM International's Materials Solutions Network, where he spearheaded the development of custom material solutions, focusing on additive manufacturing. With 20 years as a metallurgist in the automotive and aerospace sectors, Keith held key roles at General Motors, overseeing quality for global supply chain, managing over $500 million in annual steel purchases, specializing in advanced high-strength steels, laser welded coils, tailored steel products, and laser assembly. At Precision Cast Parts Corporation, he completed the management development course and contributed to advancements in forging, investment casting, alloy management, and powder metallurgy. Keith, I'm going to go ahead and turn it over to you and your team. Go ahead and take it away.
All right. Thank you very much, Jason. Covered a lot of ground in that intro there. I appreciate that. So we're going to talk today about where the material space is heading and kind of what the future of materials development is. So Jason covered a lot of my background. As he said, a very traditional training in metallurgy. Part of that was when I was with PCC. GE was a major client of ours and forced each plant to have a Lean Six Sigma black belt. And at the time, my boss didn't want to do it and sent me. So I've been doing this design of experiments, making samples, testing samples, characterizing them for most of my career. Ran metallurgy labs at a number of locations and would structure those experiments. Well, when I was at ASM, they stood up this product called the data ecosystem. And what this was a set of digital tools that they were looking to bring to their membership, focused on material science. And part of my job at that time was to kind of kick the tires on all of these different software packages. So that included ICME tools, which is Integrated Computational Materials Engineering, which we'll cover at length today. And that also included some machine learning and AI tools. So I got pretty obsessed with this pretty quick because I saw the potential for it to change the way I'd been doing my job for the last 20 years. So I started investing a lot of time in those tools, started taking some courses outside of work to learn more about machine learning, started taking some coding courses because I didn't have any background in that. And that path eventually led me to QuesTek, where we do ICME all day, every day. So at its core, what QuesTek does is we empower innovators by solving material challenges. At some point in a process or a product development, the engineering gets as good as it's going to get. And the limitation becomes the materials that you have to work with. That's part of the reason I became a materials engineer, is I've been able to work on everything from monster trucks to torpedoes and everything in between, because everything has materials issues. So our industry clients, these are a lot of people where advanced materials and material performances is critical to the success of their business. And it's the same thing on the government side. A lot of early stage research and development projects where there needs to be a material that doesn't currently exist. And that's where QuesTek comes in. So we've been doing this ICME approach to material science now for a little over 20 years. And we've patented 33 different materials, completed over 400 government contracts, another 250-ish corporate engagements. And one of the things that we brag about is that we have the first flight-approved cyber steel. And when I say cyber steel, I mean that material was designed computationally. And it was the first of its kind, designed in a modeling and simulation approach that was taken all the way to flight approval for safety critical flight applications. So really the problem that we solve is that developing new materials and deploying them is incredibly time consuming and costly. So our approach is we use physics-based models where we daisy chain these physics-based models together to create a modeling and simulation approach to what a material does during its processing. Essentially, if I know what elements are in a system and I know the energy or heat in that system, by using the laws of thermodynamics and kinetics and Gibbs free energy and enthalpy of formation and all those things together, I can create models that will determine what is going to form, what my microstructure is going to be. And if I know what my microstructure is going to be, I can use another set of physics-based models to determine the performance, the material properties associated with that microstructure, whether it be strength, electrical conductivity, toughness, hardness, you name it, all those kind of traditional material properties that we can be so focused on. And so with those physics-based models and our thermodynamics and kinetic databases, we can create models that determine how it performs. So I can do the metallurgy that I used to do in the lab, I can do it on my laptop now. And not only is that easier, but it is orders of magnitude cheaper because I don't need to process these samples. I don't need to produce them, especially in the additive space. Whenever I would do a design of experiments in additive, I'd make these samples and then they would travel all over Northeast Ohio, going to EDM, going to solution heat treating, going to machining, going out to a material testing house, coming back. Now I can do a lot of that work on a laptop. So I talked quite a bit already about this iterative approach, that's design of experiments, which is how metallurgy has been done and how it's been taught. Part of the problem with that approach is you never know when that cycle is going to end. You start, you learn, you know a little bit more, that informs your next set of experiments, and you keep doing this until you narrow in on the answer, and then you have the answer. And now I'm going to do it one more time because I got to verify that what I believe to be true is true. Okay, now I have my answer. Now I can start making products. The big difference with an ICME approach is we take out that iterative loop, right? So we plan our experiments, we understand what the design space is, what our constraints are in terms of temperatures, elements, cost, things of that nature. And then we create that physics-based chain of models that I talked about earlier. And then we start modeling that system, and I start tweaking things like heat treat temperatures, elemental compositions, right? On every material spec, there's a range, aluminum or titanium, right? Well, what happens at the min of that range or at the max? So I can model all of those things. Now, this is not without empirical data. We do use a small amount of data to calibrate those models. And that's where we really get the predictive power out of these is it's usually 10% of the materials data you would typically need to calibrate these models. So then I've created my model, I've calibrated it using traditional materials testing outputs. And now I have an answer. Okay, so now I just move to validation, right? So now I physically make it. I don't just run off and say, oh, this is a solution. I make one and verify that I was correct. And then we're done. So we can really skip right to that validation stage. So I want to talk a little bit about some areas that this has been applied and some of the success that we've had with this. So this was a really cool program. So the Navy T-45 trainer jet is the jet that the Navy uses to train its pilots on. And they had a hook shank, which is, if you guys have ever seen a video of a jet landing on an aircraft, it's the long hook that the giant bungee cord to slow the plane off of an aircraft carrier. Well, these were prematurely failing. Eyes for producing them had been destroyed and they simply could not make replacements. So the Navy came to us and said, can you design a material to meet these properties as fast as possible? Because if we don't have these hook shanks, we can't train new pilots, which was a major problem. So we designed the material computationally. We made some samples. We characterized it so we understood what the microstructure was doing. And we can also use that characterization information to calibrate those models and further increase their accuracy. And since this was a novel material, we also designed a supply chain, right? So we found the people that could execute on the various steps of the processing that was required. We worked with them. We created the technical data package for the government and managed that whole supply chain and delivered functional prototypes to the Navy. There was about 66 of them that were ready for machining. So one of the things that stands out about QuesTek is there's a number of companies that'll tell you they can do material design, and there are, but one of the big differentiators for us is that we can deliver functional prototypes at the end of the day. And to my knowledge, we're the only company that has done that successfully. So not only were we able to solve this problem of the hook shanks, but what we delivered had 20% improved power density. They were able to get 2.5 times more landing per maintenance turn. The original part, it had a cadmium coating on the outside for corrosion protection. And cadmium coatings are expensive, nasty, bad for the environment, difficult things. It's not something you do unless you absolutely have to do it. Well, we were able to build in the corrosion protection into the base alloy. So we were able to eliminate that coating, which is good for the environment, saves money, produces parts faster. It's a win all the way around. Another really cool application that we did a couple years back was the ERCA program, which was the Extended Range Cannon Artillery program, where they were trying to double the range of these howitzer style cannons that were typically mounted on the Paladin platforms. We were able to design the barrel and deliver the functional prototypes to the Army. And in early test firings, we were able to nearly double the range. We're kind of waiting to see what the next steps are. ERCA 2 was supposed to happen, and then, you guys have noticed things in the government space got a little weird over the last year. So we're, still excited to see where this goes. But if you can extend the range by double, of these cannons, it completely changes the playbook. And that's something that we're really excited to be a part of. And not only did we do the barrels, but there was a number of other components of that system where we applied a patented proprietary steel alloy to produce those. And I mean, this really was a major feat of supply chain. There was over 100 subcontractors if we look at all of these components together. One of the things that we're doing right now is, I mean, we're experts in materials science. Kind of the holy grail is, okay, how did you merge that expertise with more traditional engineering software like LS-DYNA, Magma, Deform, things of that nature? How can we inject our superior materials information into those platforms? I can't count in my career the number of times I've had problems with material cards. Sometimes the assumptions are just flat out wrong because a materials engineer was never involved in making those assumptions. Well, what if we can use our technology to put those material cards on steroids? What if instead of them being so generic, what if they're specific to your alloy, your vendor, your machinery, and then we can feed that information into LS-DYNA or Deform? It makes those good products great. So that's something that we're working on right now. There's a project funded by OSD, and we're in year 2 of that. And we're excited to see where that goes. So we talked a little bit, additive has been a big opportunity for us, mostly because, I mean, people have problems in additive, right? Additive is a different beast, and you're trying to use additive to make parts that were traditionally cast or forged. And so to meet those specifications, you use those alloys and you get a powder made of them. Well, those alloys were never optimized or tuned for additive manufacturing, which requires a very different approach than casting or forging. So we've had a lot of work over the last 6, 7, 8 years or so, developing materials for additive and taking legacy materials and tuning them so that they're printable. And personally, I've been going to AMUG for a number of years. I love additive. I got 2 home machines downstairs running it right now, making Christmas gifts. And additive is just one of the most exciting things that has happened to materials engineering in a long time. So I talked a little bit about how we tuned legacy alloys. Part of that is, we don't just work on the alloy, we also work on the process. So, what's a parameter set need to be for our machine? How much power, how fast, things of that nature to produce as dense as possible parts. And obviously, we live in a world of manufacturing. So it's not only, I can't afford to slow down to make the best, most perfect part. There's some trade-off there where I need to increase my throughput, right? So I don't need absolutely perfect parts. but I need to make them quick, and I need to balance those considerations together. And obviously, laser powder bed fusion is huge, but we do a lot in cold spray, a lot of DED. We're working on a number of different additive processes right now. So this is a really cool thing that we've been working on for a number of years, and with a little bit of luck, we hope in the next couple years or so to get it all the way up to TRL 9. So this is one of our kind of flagship alloys. This is a Ferrium alloy that we've been redesigning for printing. The original alloy was designed for rotorcraft gear transmissions. And the problem with the old material is it had a fairly low tempering temperature. Well, the thing about helicopters is from time to time they get shot at. And every once in a while, a bullet would hit a transmission case and there'd be an oil out condition. And when that occurred, the gears would get very hot, very quick, and essentially melt like butter, and said rotorcraft would fall from the sky. Well, what we designed was a new steel alloy that had a much higher tempering temperature, meaning that the amount of heat it could absorb before it started to soften was nearly double what they had been using. And so in oil runout conditions, those gears would survive considerably longer than the material they had been using. So it was kind of like a run flat for your car, where maybe you weren't going exactly where you wanted to go or as fast as you wanted to go, but you could get to where it was safe. And that's what these gears enabled, is that it gave the pilots control over where they landed and how, that they didn't have before. And so it was such a success on the Black Hawk that it has been built into the Bell V280. And I'm blanking on the name of the other competitor that wasn't selected, but our steel was also in that one from the Boeing submission. So what we've taken with that really successful gear steel is now we're doing it in additive. So let's be able to print these gears on a laser powder bed fusion machine for rapid prototyping and testing and replacements in field and all those great things that additive enables. This was another really cool thing we did. So this is a NAB, nickel aluminum bronze alloy, that we designed. What stood out on this one is at the time the Navy had been purchasing the green wire from China. China owned the supply chain for that. That's obviously problematic. And so we developed a domestic supply chain to produce the NAB wire, developed the parameter set, and then got a kind of produced a reputational prototype using that. And so you can see that propeller right there. This is something that just happened in the last year. We've been doing a lot of work in burn resistant alloys. Burn resistance is kind of a new thing to me, in my background making pickup trucks and jet engines. Never really thought about metals burning. We always thought about them melting. But metals will burn, especially in a rocket engine when you have a ton of pressure and a ton of oxygen in the environment. And so Stoke Space came to us and said, hey, we need a burn-resistant alloy that's not going to burn at these ridiculous temperatures inside of a jet engine. And we need to be able to print it, right? We're going to make all of our rocket nozzles with additive. So they came to us. We designed the alloy in about 2 months. They did some testing. We recalibrated some models, came back to them with another revision, and they qualified that material in under a year. A brand new novel alloy that hadn't existed before was qualified in under a year. That's not something you do with traditional metallurgy. It's not even close to that. And Nova and Stoke isn't interested in patenting this material. They want it to be able to be used by anyone who wants it. So this material will become publicly available for these type applications, which is good for everyone. It's good for the U.S. Defense industry. It's good for our space industry, etc. We've also had a lot of focus in the last couple of years on corrosion. Managing and dealing with corrosion is a huge issue in the Department of War. And when they don't have good information and good understanding of the mechanisms of corrosion, the answer is always over-inspection. And over-inspection is costly. It takes a lot of labor. And so we're building a tool to help them better understand corrosion so that they can reduce maintenance costs and time and effort. Talked a little bit about printability maps. This is an example of what a printability map looks like. So, I mean, what's interesting about this is I did this same exact thing when I was at ASM by DOE, right? I made samples across this design space. I'd take those samples, we cut them up. We had a CT machine, which was amazing to have a CT machine in the basement, but I mean, if you were to pay for someone to do that, you're looking at a couple grand per test on a teeny tiny little sample bar. And so I made one of these for a client using empirical methods. It took about 14 months to give them the answers. All right, here's where you need to run your EO to maximize throughput and part quality. I joined QuesTek, and I was very interested in what they were doing in the additive space because it's a passion of mine. I watched QuesTek do the same exact thing that I had done in 6 weeks. And talking to the engineers, I could have gone faster. It just wasn't a rush priority. But they did the same thing in 6 weeks that took me 14 months. And I also found out what they had charged the client for that work, which was also a fraction of what I had charged to do it empirically. So the difference with this approach is night and day. Real quick, we'll talk a little bit about ICMD. So QuesTek had historically been a kind of engineering consulting company. You come to us with your material problems, we can give you the answer. About 2.5 years ago, we launched a software package called ICMD. And what it is it's a SaaS-based software tool that contains all of our models, data, thermodynamics, and kinetics databases, all in a tool. And so people and companies can subscribe to this software and do what we do themselves. And I talked a little bit about this. And essentially, it goes back to what I described earlier about our process, is that the software, you take your inputs and you can determine your outputs. And so those are, process parameters, alloy compositions, things of that. And then you can send outputs where you can determine what impact different variables are having on the system. So this is what it looks like. When we have a little more time, I'd go through this a little more depth. So we'll go fairly quickly, but just super quick example. So I'm going to optimize an Inconel 718 plus alloy, and I want to optimize it for yield strength. So what I'm going to do is I'm going to put in those elements from the alloy specification, and then I'm going to decide what my variables are. So for this simple example, I'm going to look at aluminum and titanium, and I'm going to say, what is the minimum amount of aluminum and titanium in the specification? What is the maximum? So those are my variables, and it's what you see here. And how many steps do I want to take across that range? Well, to keep it simple, we'll just do 5. And when I run that model, now I get this output. So you'll see aluminum and titanium on the left, and I can drag a slider to highlight different ranges of aluminum and titanium, and I can see where I get my greatest total strength. So you can see there with titanium, you can see all the combinations of aluminum and titanium there and what the resultant strength is. And not only do I know what the total strength is, but I can see where that strength's coming from. So in metallurgy, there are different strengthening mechanisms in an alloy. Well, I can see how much of that strength is from precipitation and how much of it is from solid solution strengthening. To keep it simple, I left it out, but grain size would be another contribution to the total strength. So we launched this about 2.5 years ago, and these are our current subscribers. So it's been really exciting to, as a material science company, and in material science myself, get involved in launching a software package, and working with customers to make sure that, you know, there's been a number of times where there's a gap between what we thought industry wanted and what they actually wanted. Like burn resistance was an example. That wasn't a priority for us at the beginning. But a lot of the feedback we got from different space companies is what we care the most about. And so that's where we focused our efforts. We also have the software at a number of kind of science universities, and their research and academic departments are using the software for their efforts. A couple cool things that have happened over the years. So, I mean, statistically, probably half the people listening to this right now have an Apple Watch on. I mean, probably half the people have an Apple Watch on. The metallurgy required of an Apple Watch is really incredible. And Apple was the first one to do that. These products didn't exist. And now, I mean, I think I have 3 smartwatches. They give me free ones when I upgrade my phone, floating around the house. They couldn't solve the metallurgy without us. And so they bought a bunch of our technology to enable the Apple Watch. And we talked about the success story on the hook shank. Not only was the hook shank a success, but it was also fast. So historically, from white paper design to flight qualification for a brand new aerospace alloy for a safety critical application, historically it's been 20 years to get that done. We were able to do the hook shank in 7 years. And so the National Science Foundation, in conjunction with the Materials Genome Initiative, which was an Obama era initiative, have kind of put QuesTek up there as an example of this is what advanced materials engineering needs to look like. And one of the things that we did and we continue to do is this concept of accelerated insertion of materials, or AIM. So I talked a lot about how our models can predict, talking about the earlier Inconel 718 example, strength. Well, we can get more than just a nominal prediction, right? So we can put in all the variables, your tolerance on your heat treat oven, the plus or minus 100 degrees, the variation on aluminum and titanium, what the min and the maxes are. And we can put all those things into our model, and we can predict the complete range of properties that we're going to get. So we can digitally predict design allowables instead of making 300 plus samples to statistically determine design allowables. So what this enables is a number of times in my career, I've been involved in getting a material qualified for MMPDS. And it has not always been a fun project, because you would make your 3 heats of material to get your AMS data, and then you go produce another 7 heats for your MMPDS data set. And sometimes when you make those 7 heats, you find a lot of surprises that you don't fully understand where they came from. Using this modeling approach, we were able to take our AMS data and then digitally predict what was going to happen when we did our MMPDS qualification. And so now MMPDS just became a box that we needed to check off, and we were certain of the results. What that allowed us to do was start making prototypes after the AMS data set. So we were able to start prototype production while in parallel doing the MMPDS qualification. And that was probably the single biggest time saver on this project. So what I would like people to walk away from is that materials either enhance or hamper your product performance, and your materials can be a key differentiator on a process. And the traditional way to do it from a corporate perspective is no longer competitive. From a defense perspective, I mean, OSD has come out and said this a number of times that we need to lead with modeling and simulation in the materials space, because whether you consider us near peers or peers in the development of a lot of these platforms and weapons, we just can't afford to be slow any longer. And materials engineering is when I went to University of Wisconsin. I had a great time, great engineering department there. I didn't leave that school with the knowledge of any software tools other than LabVIEW for running lab equipment. There just wasn't digital tools for engineering. And if you look at any of the other engineering disciplines, every student leaves with a knowledge of a software tool that they need for their job. And that didn't exist until QuesTek brought it. And so this also dovetails into, Industry 4.0 and the digitization of manufacturing. ICMD brings that in for materials. So I thank you guys very much for your time. And I can take any questions that you may have.
All right, thank you, Keith. Great presentation. We'll now head into our Q&A session. If you have a question for Keith and you haven't done so already, you can put it in the Q&A space, or go ahead and raise your hand and I can call on you. You can ask your question yourself. So we've got one here. So let's see, Loon, if you want to go ahead. Sorry, I can't see your whole name. It says Lun. If you want to go ahead and unmute and ask your question.
Okay, yeah, thanks. Thanks, Keith. I have two questions. I think one of my questions are, there's a lot of success, especially with part qualification, being done in a year. And I think we've seen these successes, coming in a little bit more recent last couple of years. What is really done different? I mean, at the end of the day, we need to have, be able to show like strength, for example, versus compositions. Is it just a matter of being able to like project and create that data sets a lot quicker than conventional ways? Really want to hear your thoughts on what has been done different that make it possible now. My other questions is, there's also a lot of values shown on military assets, designing the Hulk, for example. Have you gotten any feedback from the OEM, original on the design, like whether they would consider taking your design tool into their next contracts for F-35, F-49, things like that? Thank you.
Yeah, great question. So I mean, on the first part, where the time savings come from is it all gets back to, I mean, in the presentation I showed a really simple experiment where I was varying aluminum and titanium and predicting the strength. So if I did that from scratch, I could come up with that answer in 45 minutes. And I could do it from a laptop. If I did it the other way, I'd have to produce the samples. I'd have to find a research and development foundry that had small scale casting that was capable of holding, super tight tolerances on aluminum and titanium, and I'd have to have them make a bunch of samples for me, and then I'd have to process them, run them through the Met Lab. And so, I mean, you're looking at months for that simple answer, assuming that you don't have those capabilities in-house, and very few people do in my experience. So what can take months empirically, I can do in hours on the laptop. So that's one big aspect. The other big aspect is de-risking, right? So, talked about making MMPDS data sets for qualification. From a de-risking perspective, I know with a high degree of certainty what the results are going to be before I do it, which is huge. I mean, I've worked on a number of MMPDS qualifications where we had to make additional heats. We had to fix something, change something, and make additional heats. And where, we sat believing to our management that this was going to take a year, well, now we fail that data set, and now it's add another 9 months to it. So it's kind of those two things in combination that really accelerate it. As far as the T45 hook shank, so we took over, so we handed the government the technical data package to produce those. So now the Navy is able to make those hook shanks anytime they want, right? All the suppliers are set up. The raw material comes from Carpenter. And so they can get those on demand. As far as the OEM that was producing them, I won't name names. They're a client. We're working with them today, not on the hook shanks, but on other material problems that they have. They've hired us, and we have a great relationship with them.
All right, thank you, Keith. All right, next up is George Barnich, and then we have, I believe it's Faisal on deck.
Hey, Keith, George Barnich here. Excellent presentation. Definitely an ICME believer. I was kind of surprised to not see anybody in the traditional defense OEMs on the list other than Boeing. There's a lot of space companies and then Boeing, but I didn't see like the Lockheeds, the Raytheons, Grumman or whatever. And it made me kind of think of what prevents people from buying seats for physics-based type software tools and stuff is generally trying to justify the cost or whatever. And I was encouraged to hear the ICMD software as a service thing, because I think that's your guys' attempt at trying to get past that, right? So if we're going to encourage a lot of the smaller tier manufacturers to step up, get creative and innovative, right, instead of tossing that responsibility to the major OEMs, they probably can't. They don't do the material development every day, you know what I mean, and got multiple people tapping licenses to justify the cost. Could you explain maybe a little bit more of, a strategy that a smaller company can use if it's got an innovative idea and wants to go down this road? And I'm kind of leading the witness here, Keith. I'm not trying to trap you or anything. I'm trying to ask you a real question here. It's really more like, can I hire a really good materials guy on a 6-month, 12-month contract basis? You know what I mean? And then get a license for this. And then all of a sudden let all the magic happen, and then I punt because I'm not doing material development.
You don't need it anymore.
You know what I mean?
Yeah. Because now you're in the game of manufacturing, right?
Exactly.
Now, right. Yeah. So, I probably should update my slides. We just started. We have 2 projects running right now with Lockheed. They're great. And we've done some projects with RTX in the past. We don't have a current one right now. So, those are companies that we're interacting with. Hope to have a joint proposal go in with Lockheed here in the next couple of weeks. They're fantastic to work with. So pretty much all of the big OEMs we're interfacing with in one way or another, or we have in our past. Your question about the small companies and how do you bring this tech to a small company? So I've had an interesting career in that I've worked for huge corporations like PCC and General Motors, and then tiny ones like ASM and QuesTek. And so I feel you on, how do you bring this? One of my favorite things about QuesTek is we're really flexible on how we work with clients, and we just kind of have this buffet of options. You talk about being able to hire somebody for 6 to 9 months. We do that all the time. We still do engineering as a service. And I tell you who does that a lot. We get and I can't name the teams, which as a gearhead bothers me. But F1 comes to us a lot and says, I need this part. I need it additive. I'm making 4 of these. Time is of the essence. We have 2 people on staff that understand materials, and they're in charge of understanding, 300 different advanced materials that this F1 car uses. Can you just give us the answer? And so we do that. We say, okay, this is how you heat treat this aluminum alloy to do X. So that is still a service we do, and we're happy to do it. And that's one way we engage with smaller clients. As far as bringing it to a company, there's 2 ways. So we do, when we bring somebody on board and there's a new subscriber, we do run a software training workshop that I originally designed for the company, because I'm not a ICME engineer. There wasn't such a thing at Wisconsin when I was there, and I don't have a coding background. I'm just a metallurgist. So we designed a curriculum for a materials person or a mechanical engineer with materials responsibility, because that's about half of the people that are dealing with materials, to be able to run this software themselves. And so there's training, and then there's in the software, there's a bunch of workshops and tutorials built in there so that you can educate yourselves. And then obviously, there's support from the QuesTek side in terms of training and development. And there's all these gradients in between. We had one client that was like, I want you to develop these models. It was a burn resistant. Develop them, put them in the software, and it wasn't in there at the time. And our staff on how to use it. And we did that. So I hope I answered your question.
Good enough. Thanks.
All right. Thanks, Keith. All right. So Faisal, if you want to go ahead and come off mute and ask your question. I did see your question in the Q&A, but I thought Keith might have answered it when he was answering his first question. But if you still have a question, come on off mute and go ahead and ask.
Thanks, Jason. Hi, Keith. My name is Fazal from Canada Phase Shift Technologies. We do a ton of alloy design as well, so always on the lookout for new computational solutions that can help us get to our goals faster. My question is still along the same lines that, with what we have seen with a lot of computational tools is that they help us get to a chemistry faster, but for some of the standardized qualification, it still takes the time it takes to test out a material. So really curious how we could potentially reduce the time it takes to qualify a material. That's
I think I lost you there.
Sorry, can you hear me now?
So I believe the question was around, okay, well, we still have to do the material testing for qualification.
Correct.
And yeah, you do. Now, so we have good communications and good relationship with the folks at Battelle that run MMPDS, and there's conversations of, when can modeling and simulation start to replace some of these things? I don't know. I wouldn't make a bet whether it happens during my career or not. Who knows? But what it does do is it goes back to that de-risking. Of knowing what the answer is, and if you know what your AB basis design allowables are digitally, using that to give that to your product engineers, your design engineers, so that they can start designing products, making prototypes, and de-risking those qualification efforts. But no, to be very clear, this is not a substitution for MMPDS data. It's a predictive tool for MMPDS. Using that as an example because that's what is closest to my heart.
Sounds good. Thanks, Keith.
All right, thank you. All right, we have one from, I believe it's Sujit. If you want to come off mute and ask your question.
Hey, Keith, thank you very much for an amazing presentation. So can you please help us understand the grain development in additive manufacturing as the part is being built? so that maybe we can try to understand thermal gradients better? Does the software allow for characterization of how the part characteristics will be with various forms of additive manufacturing?
Yeah. So, I mean, that was a big question of mine, right? So, I mean, I started my career at Mercury Marine in aluminum die casting. And so, you know, pouring in a bunch of hot metal and controlling how it cools, yeah, I had my head around that. But I mean, this additive business, I'm laying down these little tiny weld beads and stacking up weld beads until I make a shape, right? So how do you account for that? So the technology pretty much stays the same, except there's a loop in there of an FEM engine, right? And so that FEM engine takes into account that rapid solidification, the stacking of thermal gradients, the penetration from one layer down into another in terms of heat. So there's a FEM engine in that loop, and that's how we do that. So like when I talk about calibration data, the big calibration data we need to produce like that parameter map that I showed earlier, it's single track weld beads, right? So I need to know for a given laser power and speed, how big my how wide my weld bead was and how deep it was, how much penetration I had. And then I can feed those 2 points of calibration FEM engine, and now I can digitally characterize that additive process. And I'm using laser powder bed fusion because it's kind of the most straightforward example. And it gets a little bit more interesting on like AFSD applications, additive friction stir. But additive friction stir doesn't have nearly the market penetration that laser powder bed fusion does. So does that answer your question?
Yeah, can I just elaborate a little bit more? So I'm looking to use laser wire for space manufacturing, in space manufacturing. And there are some constraints which are like vacuum, deep vacuum, and also something like gravity and the weld bead flow, because that is what will continue the process. How can your system help me to do that without engaging supercomputers? Because that's my current solution.
Yeah, so microgravity and material production is, I mean, that's a pretty niche thing right now. If we can have a deeper conversation on that. We are currently just about to kick off a program with NASA and the NASA Ignite program to look at how microgravity, low gravity impacts what we know about materials production. So we had enough of a concept there, and I'm drawing a blank right now on what university we're partnered with on that. But it's not something we have a background in, but it's something that we're working on right now.
I appreciate it. I'll touch base with you offline.
Yeah.
Thank you.
All right. I think we got one more. John Martin, you want to come off mute and ask your question?
Yeah, sure. Thanks, Jason. Hey, Keith, great presentation. This is great information. So as Jason mentioned, I'm John Martin. I work for NCDMM on the America Makes program. So one of the questions that comes up, or, you know, one of the things we think about when we talk about this is so I wanted to ask you, like, is there any scenarios or existing scenarios or path forward, if there isn't, on developing an alloy that maybe is going to be more broadly used, and then kind of something that could have a large impact to the industrial base instead. I don't want to call it a point solution, but like these custom alloys that maybe are patented or held internally by companies or licensed, and it's, you know, creates some issues for some of the folks that are willing to adopt some of this stuff within government. Or just in general, kind of constrains things. So it's like a balance of trying to keep everyone happy and make money, but also, you know, open the floodgates for at least some of these alloys. I guess just kind of what's your opinion on that at the current state?
Yeah, I mean, it's a problem. It's been a problem my entire career. And so the issue is company X, I won't name names, but they sink millions of dollars into developing an alloy, characterizing it, understanding it fully, just years and years and years and years of effort. And then as a materials community, we say, well, if we could all share our data, we could go much faster. And, smaller companies that want their hands on Alloy X could more quickly implement that and not have to reproduce data that's already been done. And everybody talks about it, and you never see anything meaningful in terms of that data sharing. And then actually the only one example, the first example where I've actually seen some of that information shared across the community is America Makes. I remember some of the additive information and using it on a project when I was at ASM because we were members. So I have seen that there, but that's the exception, not the rule. What is promising about these digital tools is now the lift to get to these materials is much lower, right? And so Stoke is a fine example of that. Stoke didn't invest millions and millions and decades developing that alloy. They paid a fraction of that and spent a year working on it. And so anybody can use that alloy. And I mean, the reason Novaloy, and I don't think this is public yet, but I believe it's going to be called Novaloy when it gets commercialized. The reason that's developed is because there were alloys at other space companies that exist and did what Stoke needed them to do, but they were patented and proprietary. So Stoke had to start from scratch. So as we get more digital and we're able to do these things faster, I believe that's going to help with that. And then also Matt Draper at OSD, some of the programs that he's running in a very meaningful way are going to start distributing large scale materials testing data for alloys critical to the Department of War. That's going to take a few years to get online, but there's a plan there to make that happen.
Okay. All right. Yeah. Thank you very much.
All right. Thanks for that, Keith. I think we might have time for one more. I'm not going to read the whole question. It's there in the chat, but it's around polymer blends or composites. Has your team at QuesTek explored those, and do you work with those as well?
Yeah, so polymers is kind of a hard no. I always kind of like, so my metallurgy apparently wasn't trendy enough. So I'm not a metallurgist. I'm a material science and engineering, broader materials, and obviously polymers being part of that. But I don't know anything about polymers, and the few times I've gotten involved, they're way too complicated compared to what I know from a metallurgical standpoint. So we really don't deal with polymers. There is a company that I'm a big fan of called Schrodinger, as in, Schrodinger's cat, that essentially is what we do, just in the polymer and pharmaceutical space. And they're really cool, and they're very similar approach with us, just on a different material. On the ceramics, we dabble. We have done some projects with ceramic metal composites, and we have done some work in functionally graded materials. And some of the high entropy alloys, there's some Venn diagram overlap there. So if anyone's interested in a ceramics thing, that's kind of a case by case basis, where on the metal alloy side, the answer is, 99%. Other than the exception of microgravity, the answer 99% of the time is yes.
All right, great. Thanks for that, Keith. All right, thank you for all your questions. Keith, thank you for doing your best to answer those completely. So that's going to wrap up today's NCDMM Alliance Partner Lunch and Learn. I'd like to thank Keith Fritz and QuesTek once again for that great presentation. If you have further questions for them, please reach out directly at the email on your screen or the mobile number. And as a reminder, if you or your organization is interested in becoming an NCDMM Alliance partner, you can navigate to ncdmm.org under Who We Are and click on Our Partners, or you can go ahead and just click on the link that I shared in the chat earlier, and that will take you to the form. Thank you once again for joining today's NCDMM Alliance Partner Lunch and Learn. Everyone have a great afternoon. Thanks again, Keith.
Thank you.
Bye, everyone.